Hello, beautiful people. Remember our big O of n squared approach to solving this problem? Yeah, well, pretty simple. We have tried out each and every subarray, but we were able to update the number of distinct values in that subarray in constant time, which is super cool. Now, there is one optimization that I can actually make to this code, so let me write it and I'll get back to you. And here is the optimization, only this line of code. Now, what does it do? Well, it's pretty simple. When we are trying out the subarray I, j, and the number of distinct integers there is not less than or equal to k, so obviously is greater than k, then I'm going to break out of this for loop. Why do I do that? Well, it is pretty simple. If I have one subarray, let's say starts at I, ends at j, and in this subarray, I already have a number of distinct integers greater than k. What's the point in trying out greater j's? When I will try out greater j's, I will basically push to this current subarray new values. And when I push new values, obviously the number of distinct integers can only get increased, right? So if I already have here a number of distinct integers greater than k, obviously if I take this subarray or this subarray, or every one on its right, I'm going to have a number of distinct integers also greater than k. So they are not going to be valid. So why even take them into account? This is good. This optimization is definitely going to decrease the number of iterations our algorithm does on some examples, on some inputs. But remember that in order to really conclude that an algorithm has a specific time complexity, we need to take into account even the worst case scenarios. And in the worst case scenario, the number of iterations is the same. Very simple. Imagine you'll have an array of integers, right? And integers, and you can even imagine that all of them are distinct. So 1, 2, 3, I don't know, n minus 1 and n. And let's say k equals n. Now, in this scenario, no matter what is the value of I, you can start with I from here. You are going to try out each and every j until the last element. And why is that? Because all the subarrays are valid. If you go with I here, again, you're going to try out each and every j until the last position. So in the worst case scenario, we will actually never execute this line of code even if we have written it. But that's not the point. The point of this line of code is to actually ring a bell to us and tell us that maybe I can apply the two-pointer technique here. Because remember, when solving problems where we have to count the number of valid subarrays or find the longest valid subarray or stuff like that, and we find out that once a current subarray is not valid anymore, all the others are also not valid anymore, 99% of the time, we will be able to make the two pointers technique optimization. With this new line of code, what we are doing is that basically for each value of I that we try out, we are going to try out each and every j until we find one that is bad and we stop and move to the next I. So basically for each value of I, we are computing that max j. For each I in this algorithm here, we are computing the max j of I. And remember, the max j of I is the greatest j such that the subarray that starts on position I, so such that nums of I and j is valid, right? Nums of I and j is going to be valid, and obviously nums of I and j plus 1 is not going to be valid anymore. This is the definition of max j. What we do is that for each value of I, we first compute the value of max j of I, and then of course, we know the longest valid subarray that starts there on position I, and we are going to update the answer with max j of I minus I plus 1 if this is greater than the current value of the answer. So our purpose here is that for each value of I, we need to compute very quick what is max j of I. How we do this in this algorithm is that for each new value of I, we start again with j equals I and just increment the j as long as it is good. And once it is bad, we are not going to do anything anymore. But the two pointers technique tells us that we can use the fact that we have already computed max j of I minus 1 and just continue from there in order to compute the max j of I. Let's see how it works for an example on this problem. And I have chosen this example to show you better how this works. So we start by trying out I equals 0. For I equals 0, what I'm going to do is, of course, find its max j. So try out each and every j until I encounter the first bad one, right? So I try out j equals 0. I have this subarray, only one distinct element. Everything is good. Then what will I do? I'm going to increment the j. So j is going to be here. I have two distinct elements, still good. Our k equals 3. Then I'm going to increment the j again. I have this subarray, 1, 2, 4, 3 elements, everything good. Increment the j. I have this subarray, 3 elements, everything good. Increment j. And I'm going to have this subarray, 1, 2, 4, 2, 3, where unfortunately I have 4 distinct elements. So this is the first bad j, which means that I need to go one step back, and this was the greatest j such that in the subarray nums of 0 and this j I have at most 3 distinct integers. So what is max j of 0? Max j of 0 is 0, 1, 2, 3, the value 3. Cool. Now, what do I do now? After having computed the max j for I equals 0, I will, of course, update the answer with this length if it is greater than the current answer. And because the current answer is 0, answer will become equal to 4. Awesome. Now, I finished I equals 0. I have to move to I equals 1. And this is what I do. Now, when I go to I equals 1, again, our brute force approach would have started with j from I and would have tried out each and every j until it encounters the first bad one. But let's stay with j where it is, because if we know that this subarray with I equals 0 was a valid one, of course that this subarray is going to be also valid, because it can have a number of distinct integers less than or equal than the previous subarray. And it actually did. As you can see here, the number of distinct integers is 2. So I know this subarray is valid. There is no point in trying out this subarray where j equals I or this subarray where j equals I plus 1. I know they are valid, obviously, but they are shorter than the one that I have here. So why would I even bother, right? So I know this one is a valid one, but I also know that maybe I have some greater j's which are still good. So I'm going to try the next one. And what do? I move with j here. What's the number of distinct integers here? 2, 4, 2, 3 is 3. It is good. Awesome. So I try out the next j. 2, 4, and 3 are the distinct integers. Still good. So I move to the next j. And here on this j, I see that my subarray has a number of distinct integers equals to 4, which is not good. So what I'm going to do is move one step back, and I know that this is the greatest valid j for I equals 1. So I have just found the max j of 1. Max j of 1 is going to be equal to 0, 1, 2, 3, 4, 5. Yeah. What do? I know that this is the longest subarray. This one is the longest subarray that starts at position 1. Its length is 5. It is greater than the answer, so the answer will become 5. See what I did there? Because the fundamental property of the 2 pointers technique is satisfied in this scenario, I can keep j as it is, and when I move to the next I am only going to try out greater j's. Again, let's take one more I, and let's say that after finishing this value of I am, of course, going to try out this value of I. Now, again, because I knew that this subarray was valid, of course, I'm going to know that this one, I and j, is going to be also valid. So what I'm going to do is that, of course, I'm going to try to find better ones. I increment j. It is here. And unfortunately, I have 4 distinct values. So this one is not a good j. So I need to take one step back, remain with j here, and max j of 2 unfortunately didn't get increased, but it is still equal to 5. Right? So max j of 2 equals 5. Of course, the length of this subarray is 4, so the answer is going to be still 5. Awesome. Now, next step. Of course, I'm going to try out the next I, right? So the next value of I is going to be this one. Again, because the previous subarray was a valid one, this one, 2, 3, 3, is also a valid one. And I will just try out greater j's. This j, yeah, 3 distinct values, all good. This j, yep, still 3 distinct values, all good. This j, well, obviously no, because I got out of the array. So I move one step back, and I can conclude that max j of, what's the value of this I? 3. So max j of 3 is going to be equal to, what do I have here? I think I have 7. Yeah, it's going to be equal to 7. So what's the length of this? It is 5. Answer is going to be equal to 5. And of course, no point in trying out the other i's, as I'm just going to have shorter and shorter subarrays. And this is it, guys. This is how the 2 pointers technique works here. Again, if you want the mathematical proof, you can do it. You have seen how I proved it on the previous problem, but that's no worry if you don't want the mathematical proof. It is just the fact that if this I, j is a valid one, so it has at most k distinct integers. When I move to I plus 1, of course, this one is also a valid one. So I'm just going to start off with this solution, and I'm just going to try to extend my subarray. Cool. Now let's see how the code looks like, analyze one more time the time complexity, and finish this problem. All right, and here is the code. First of all, I know it is a little bit more complex than what we are used to, but don't worry, I'm going to make it simple for you. So first thing I want to note here is that this piece of code comes right after this one. So the for loop is right after this line of code. Obviously, I didn't have enough space to write it one after another, so that's why I split it in two. Awesome. Now, in the first part of the code here, what I do is that I find the longest subarray, which is valid, of course, and has its left point in 0. So obviously, I'm going to need to use my hash table, number of occurrences, which is going to count for how many times each value appears in my current subarray, and I'm going to need my variable counter to actually know that number. And what do? I try out each and every j from 0 to n minus 1, and for each j, I first insert this new element into my subarray. So you've probably noticed I use here two functions, insert and remove, which are going to be implemented by ourselves. We are going to see that in a minute, but what you should know now is that the insert function is used in order to insert a new element into our current subarray, and of course update the hash table and the counter variable accordingly, so I know what is the new number of distinct integers. So I insert this element, and of course, because I have inserted a new element, the counter could have gotten greater, so I have to check. Is the counter now greater than k? And if it is, I'm gonna break, because I've just found the first bad j for this I equals 0. Now, when I exit this for loop, and I'm here, we have two possible scenarios. Remember, then whenever you have a break inside a loop, when you exit that loop, you could have actually exited in two manners. The first one is we exit through here, so the counter is greater than k. So indeed, we have found a j which is bad, so we should move one step back. So if counter is greater than k, I should move one step back, j minus equals 1. But before that, of course, I have to remove that value from our hash table. Cool. So this is exactly what's for. And the second scenario is that we have just exited this for loop naturally, and j became equal to n. And now that I think about it, I actually made a mistake here. This j being decremented should have been placed here, because even if we exit this naturally, so j equals n, of course, I will still need to decrease the j in order to make it valid, right? To not exceed the array's boundaries. So, cool. No matter what happens, I'm going to initialize my answer with j minus I plus 1, because this is the first valid subarray that I've just found. Now, I'm going to continue the algorithm and actually try out each and every left point which is greater than or equal to 1. So for each I in this range, what I should do first is, of course, remove nums of I minus 1 from our hash table and update the counter, right? Because we don't have that element anymore. Then I keep j where it is, and I try to increment it as much as I can so that the subarray nums of I and j stays valid. So while j is less than n minus 1, I'm going to increment it. I'm going to insert the new value into the hash table and update the counter, and if the counter became greater than k, I'm gonna break. Again, after I exit the while loop, I could have exited in two possible manners. The first one is through this break, which means that j is actually bad, so I need to go one step back. So if counter is greater than k, this is how you check, by the way, whether you've exited through this break. If counter is greater than k, I'm gonna remove that element and, of course, decrement j. If not, cool. That means that j is equal to n minus 1, and of course, I don't have any new elements to add into my subarray. So what I'll do, I'll just update the answer no matter what happened. I'll just update the answer with this subarray because I know it is valid. And of course, at the end of the algorithm, I just return the answer. Now, let's take a look at the insert and remove functions. And here are the functions. Let's start with the first one, insert val. Remember that whenever we insert a new value into our subarray, the number of distinct integers could get incremented, right? Because if that value is not part of the array already, of course, I'm going to have a new one. So, in order to check this, I'm going to check if the number of occurrences of val is 0. And if so, this means that this is a new value and I'm going to increment the counter. If not, I'm just going to leave the counter like this. Afterwards, of course, I'm going to increment the number of occurrences of val. Now, the second function, remove val, is the exact same, but this time, when we remove a value from the subarray, the number of distinct integers could actually get decremented. And think about it. If in our subarray we have only one value of 2, and we remove that value, we're not going to have that value anymore, so the number of distinct integers gets decremented. And this is what I do here. If the number of occurrences of val is 1, this means that I should decrement the counter, and then obviously I'm going to decrement the number of occurrences of val. And this is all, guys. Now, what is the time complexity of these functions? Well, it's pretty simple. Everything we do here are just accesses and modifying the pairs inside the hash table. So both of them are big O of 1. They execute in constant time. The pen doesn't work. Anyways, they execute in constant time. Now, let's return to the main algorithm and analyze its time complexity. Now, back to the main algorithm, let's analyze the atomic operations. I have this, which is constant, insert. We know that the function executes in constant time, constant, this too, also constant. All right. So the first piece of the code, let's think about it. Constant operations, and then I have a for loop, which does at most n iterations, right? So I can say this is big O of n. I can have an upper bound here. All of these are constants. Yeah. So the first piece of code is big O of n. Cool. Now, let's go and analyze the second one. For the second one, I have this for loop, constant. All of these are constants. All of these are constants, and these are constants. So what is important here is that I have a for loop and a while loop inside it. Again, don't fall into the trap to say that this is big O of n squared because we have two nested loops. We know that this is a two pointers technique, and we know that I takes each and every value from 0 to n minus 1. And we also know, although the number of iterations in this while loop is not constant, it depends on the context, we know that in total, j is going to be incremented for at most n times. So j also is going to be incremented for at most n times. So still goes from 0 to n minus 1. So each element in the array is going to be visited exactly twice, one with y and one with j, and is going to be inserted and removed, let's say, for at most 2 times. This being constants, everything in rest being constant. Also, the second part of the algorithm is big O of n. So our final time complexity here is big O of n, guys. Again, I want to congratulate you. Thanks for being here. This was a hard problem, and you being here and making sure that you're gonna understand it is amazing, because not only you're gonna be able to solve each and every problem like this, trust me, they don't get much harder. This is one of the hardest problems on the two pointers technique. And yeah, it proves me that you are a very good student and you are willing to put in the work. Again, enjoy coding, and I'll see you on the next one. Bye.